good afternoon. Welcome. My name is Jerome Dochez, and I'm the build system lead at Google.
Hi, I'm Leo Say. I'm a product manager on the Android team.
And I'm Xavier Ducrohet. I'm a lead for the developer tools. OK, let's start with what we worked on last year. So the very first thing that we did was, we've been working on namespaced resources. Jerome and I actually stood here last year, and we talked a lot about namespaced resources. And sadly, it has not shipped yet. We have gotten a lot of feedback from you, and we're very happy for that. Thank you. As we kept working on it, we realized a couple of things. The first one is we needed more features from Gradle in order to efficiently process ARs that are not namespace enabled, but you still want to consume in a namespace module. So we've been working with the Gradle team very closely over the last years, and we got that done, so it's now available in Gradle. The second thing that we realized is that Studio needed a lot of work. Studio has its own understanding of resources. It parses all your files as you change them. It builds its own index, and that is used for code completion, resource references for navigation, as well as rendering. And so we needed to update this to be able to handle both namespace projects and non-namespace projects. And then you're all aware of Project Marble. So, the last 6 months, we've been working mostly on quality and not on new features, and so all of that was put on hold. And so as soon as Marble is done, then we'll keep working on that, and we'll be able to hopefully ship namespace resources soon. In the meantime, we have made some small improvements to the resource pipeline processing. One of them, for example, in library resources, we directly generate the R class as class files rather than Java code that needs to be compiled in order to reduce the strain on the Java compilation. We have a few more changes that have been going in master very recently that will be shipping probably in 3.6.
All right. Let's talk a little bit about multi-threading in the Android Gradle plugin. So for a few years, we've encouraged users to go modular because some modules can be built in parallel. That's true because all interactions between some modules have to be done through files, so there's no side effects, no side channels, so it's really good. Unfortunately, that's not true when you're talking about a single module, right? So basically what happens is that Gradle has to run every single task sequentially. So obviously, we've tried to optimize things by using executor services and trying to shard the implementation of some of our tasks, but it doesn't really fix the entire issue. And on top of that, we have executor services, other plugins. They have other executor services. Gradle Daemon has its own executor services. So the result is that we tend to overwhelm the build machines when we run builds. So that's really not good. So to solve this problem, we've worked with Gradle on a new API, which is called the workers. The workers are side effect free because you have to basically serialize all the input parameters to every work item, and it's going to be deserialized when the work item is going to execute. So that means that if you change the parameters after the submission, the submittee will never see those changes. So there's no side effect. Gradle can also much better maintain the number of threads being used and the workload, so you're sure that you're not going to theoretically overwhelm the machine anymore. And on top of that, it's relatively easy to retrofit classes to use workers. So we've been quite busy at doing this, but let's look at how this impacts the build by using workers. So here we've got a single module. It has 3 tasks, A, and you've got B and C's, which depends on A. So on top of these graphics, it's what's happening today when you don't use workers, right? So you've got the 3 tasks that have to execute sequentially. Now, when you use a worker, like you can see that the task B is spawning a worker. As soon as the worker is being spawned, because there's no side effect possible any longer, Gradle is capable of electing a new task for execution. So here, task C can start executing on a different thread as the worker for B is completing. So obviously, it's very positive because T2 in this particular case is much before T1. So now if you do more and more of this, you can imagine that now there's going to be more and more threads being used throughout the build. Unfortunately, you can end up in a situation which is not exactly what you wanted. In particular, workers are an implementation detail of your task implementation. So basically, that means that there is no decoration. Gradle does not know if your task is going to be using workers or if it's not going to be workers. So it cannot select your task just because it seems it's going to be faster. So in this particular case, it decided to schedule task C before task B. Nothing prevents it from doing that. And when that happens, well, we fall back into where we started, really, because the task C executes first, because there's no other possible parallelism that can happen. The task B will have to wait for task C to be finished, and then the workers will be spawned, but at that point, there's nothing less. So nothing else to be run, so basically, you end up exactly in the same situation as you started from. So it's not that great, right? So to fix this is basically to switch all of your tasks to use workers. Because at that point, if you go back to task B being executed first, you can see that the task C being scheduled as soon as the worker for the task B starts. Because you have a worker C, it really does not impact the overall build time. But if Gradle decides that he wants to schedule task C first, you can see now that the task B will complete a lot earlier than what we've seen before, right? So this is a very brief description, but basically what is important to realize is that if you have yourself tasks that you've wrote, if you have yourself a plugin, you really, really should consider switching all of your tasks to use workers. We have converted 90% of the Gradle plugin tasks to workers, so that means we are ready to play well with each other and also with ourselves, because we've seen that as we were switching some of our tasks to workers, we actually accelerated overall build time, especially for projects that have a very few number of modules or even like a single module. So we can start making things more in parallel. It's on by default in 3.5, so you don't have to do anything, except if you use Kotlin. If you use Kotlin, and in particular if you use annotations processes, you need to turn it on for KAPT to be able to leverage the feature. I suspect it's going to be on by default pretty soon, but so far you have to do it manually.
OK, so one of the things that we've worked a lot is artifact transform. So artifact transform are a way to process dependencies. During configuration of a project, we don't have access to the dependency graph, so we don't know how many artifacts you're going to be consuming, because it takes time to resolve the dependencies. And so we cannot create a per dependency task in case we want to process dependencies to do extract ARs or predexing or things like that. So this is a new API that was introduced actually a little while back that we've been using since 3.0. We work very closely with Gradle again. And we've been using that since 3.0 in order to extract AR in a more efficient way than we used to do before. Unfortunately, the API was not enough to enable us to do things like predexing and desugaring. And there's a couple of reasons for that. One of them, it did not allow incremental inputs. It did not really support caching. And the other thing is that the scheduling was not very good. It used to run as soon, just before the output of the transform was needed, rather than work as soon as the input of the transform was ready. So in terms of predexing, that new scheduling is going to give us a lot of benefits. So we've been starting to use that for predexing and desugaring, and I'm going to show you a little bit what that looks like. So this is a Chrome trace output. Jerome will talk about this output in a little bit. And what we have here is a project with about 100 modules running on a machine with a lot of cores. And every little square is basically a task happening in one of the modules. And so what you can see here without artifact transform is, in order for us to schedule predexing, we kind of have to wait until all the modules are ready and have been built for us to have a task that consumes all of those outputs and then start doing the predexing. And in fact, we do it with the dexing of the main app. And so you can see this task here toward the end that's taking a lot of time, and also during a time where we can't do that much processing because it's very at the end of the project, in the app, when all you're done is basically packaging and dex merging and do a few things. So with transforms, we can schedule that, or Gradle schedule that for us much earlier. And as soon as a module generates its jar, it can schedule the predexing library. And it can be cached on its own, so you have much more caching granularity because you don't cache the whole task that does all the predexing. So just on this module, on this project, with 100 modules, you can see that a clean build is improved by 15% by this introduction. Another thing that we've been working on a lot is lazy task configuration. We've been working on for quite a while, but we've basically made everything lazy, well, mostly. And we wanted to kind of show you the impact that it can have. So on the left side, you have the same exact module, 100 module projects. And you can see that if you run it without lazy task, we configure almost 19,000 tasks. That's a lot of tasks to configure. And on the right side, with the right flag on, we only configure about 3,000, 2,400 of which are actually needed by the build. And there's a little bit under 800 actually created eagerly. This is a bug that we need to fix in our plugin. A few of them are actually needed, some of them are not. And when you look in detail at the time, you can see that configuration goes from 1.8 seconds to about 1 second. But then you also have some of that time lost back in the graph calculation, right? So what's happening is that as Gradle built a task graph of all the tasks to execute, it realized that, well, it needs to configure those. But overall, we're still gaining about 25% configuration time on this project.
So another thing that we talked about a lot last year was incremental annotation processing. So again, with Gradle, we worked on implementing the ability to have incremental compilation even when there is annotation processors on the class bus. This has been delivered, so now we have the ability to run incremental. Obviously, this is dependent on annotation processors to play well. And here we have a list of the top 10 annotation processors as we see being used through our performance data. And we've already converted 6 of them, and we're still working on the 4 remaining ones. We will continue monitoring this list of most used annotation processors, at least open source ones, and we will try to convert them as much as we can. But you have to be careful, again, that if you have your own annotation processors, it's very important that you make the effort to make it incremental capable. Usually, it's not very complicated. One thing that we also did as part of this work is to make sure we blame correctly the annotation processors which are being configured and that are not incremental capable, so that if you are a provider of an annotation processor, you will start getting some, maybe angry emails from your users that, why is your annotation processor not capable of handling incremental compilation yet? So if you see things which are open source, please talk to the author. If you think which are in-house, you will have to fix it yourself, obviously. We also have a page on our documentation that lists all of the annotation processors that were converted on this list, plus some other ones which are not in the top 10. The version at which they started being incremental capable, and we also list the ones and the plans that we have. Feel free to send us email if you want us to add some stuff there, but it's basically the reference about what's available today. And since we were at it, we also added support for Kotlin, obviously. So now if you use Kotlin and you have annotation processors, we also have the ability to run KPT in incremental mode. It's dependent, obviously, on the same annotation processors being incremental. But as you can see on those graphs, the numbers are pretty impressive. We are really continuing to push forward incrementality as being a very important feature of the Gradle plugin.
OK, so one other thing that we did is we tried to improve the performance of sync inside Studio. A lot of the time spent when you import a project is actually spent in Gradle. And so if you look at the old sync that we had before, the first thing that we need to do is build that model, right? We need to query Gradle in order to know which module you have, what are the properties, and what's the dependency between module and external libraries. And so we have to call Gradle, which configures your projects. Because we need dependencies, we resolve the dependency, and then we query that model. The model query is actually very quick. And then, well, Android relies a lot on generated source code, right? Your R class, AIDL, run the script. So we always call into another build that configures again, resolve dependency, and then run some tasks. So we worked closely again with Gradle in order to contribute some changes to the tooling API of Gradle in order to be able to do both in the same build. So now we can do only one single configuration. We can do one dependency resolution. Then we query the model. And during the query of the model, as we query it and we process it inside our plugin, we accumulate the list of tasks that represent generating sources. And then we schedule them. And then Gradle will run them after. We also did a change here because Studio now is able to create virtual classes for R. Right? So as I mentioned earlier, Studio is parsing your dependency, your resource file as you edit them, and it always knows what's going on. And so it's creating some virtual R classes so that it doesn't have to rely on the build. So if you add a string to your file, you don't have to build in order to update your R class. It's just done virtually for you. And so since we do that, we don't have to build it anymore. So as you sync, the post-sync build, which is now integrated, just does not run that task, and therefore you have a faster sync as well.
So another thing we launched, as you may have heard, is apply changes. And this enables you to make small edits and deploy while keeping your app in its state. This is actually pretty fast because it does not restart the app. But unlike Instant Run, which some of you may know, it does not modify the build. Instead, it redefines the classes on the fly and uses some new runtime instrumentation from the platform. Because it depends on this new runtime instrumentation, it's only available for devices running Android 8 and above. It works best when you're making really small changes inside a class or making small edit to our resources. But as you may have heard from Tor earlier today, this project also brought a lot of improvement for every build. We also looked at the build output window and tried to improve it. We improved the UI and also the underlying parser to really make sure that all of your build errors show up as a node in this window. We extract the relevant information to make sure that you have a file information, line pointers, the details on the error. And we improved the UI a little bit to expand the tree, scroll, and select the error node automatically. This is a small change, but we hope it makes your life easier. So as you can see, we've been, go for build output window. So as you can see, we've been pretty busy adding a lot of new stuff to the build system. But I cannot talk about build without mentioning build speed. So let me deep dive into this a bit, because it's really one of our top priorities. First, let me set the stage. To measure build speed internally, we use a set of benchmarks. We use some open source projects like SanaTracker, MinSDK 15, and 28 for multidexing, and another one called Takeomi and Signal. But those are small-ish. So we really wanted to test on large projects. So we generated 2 projects, one with about 100 modules, 97 to be precise, and 50 of everything per module, so 15 classes, 50 layout, etc. We also created an equivalent project of the same size, but all squeezed into one module. And both of those projects have 200 external dependencies. And every time we make a change to the build plugin, we run those projects on various scenarios. So let me walk you through some of those. One scenario is to make a code change. So we change a little bit of code and rebuild the project. On the open source project, you can see some improvement ranging from 24 to 36% improvement between 3.1 and 3.5. When we looked at the 2 very large projects, and here the legend is large 100 is the one with 100 module, and large 1 is the one where everything is squeezed into one module. You can see that we improved by between 50 and 80%. In other words, here we divided the build speed by 2 on the large project with a lot of modules, and by 5 on the single module one. The big improvement in 3.4 here is largely related to the Java-C incrementality that was added, or that was improved. All right, another scenario we run is making change to resources, because that happens. And so here again on the open source project, we can see improvement ranging from 26 to 53%. And in the large project, we also see good improvements ranging in the 30-ish%. So those are 2 important scenarios, editing a source code or editing resources. There's others that we ran on. And when we aggregate the scenarios that I just showed you, we saw an average build speed improvement by 35% between 3.1 and 3.5. All right, so far we're happy. But we also look at real build speed. That's the one that's experienced by all of you. And we do this by aggregating data that all of you, or the one of you that share with us when you opt into sharing usage statistics with us. And so here, shameless plug, if you do not, please opt in. It's aggregated and it helps us a ton, and it's in the system settings. So when we aggregate those data, we see that the median build speed increased by 25% in the last year-ish. Note, though, that this is not really showing the improvement from 3.4, which just went stable a couple weeks ago, as well as 3.5, which just went beta yesterday. So now I show you some graph going down, some graph going up. You may be starting wondering why. Well, the reason is that while our benchmark projects are pretty static, your real projects are growing. You're adding line of code, you're adding features, you're adding new Gradle plugin, and this growth impacts your build speed. So if you're trying to reconciliate these graphs going down and up, let me walk you through a real-life example. Looking at Spotify, in the last year and a half, the project grew by 25% when you're looking at line of code, and 230% when looking at modules. That's about 3x the growth in a year and a half. It's huge. At the same time, clean beat slowed down by 38%. So I'm going to normalize using line of code growth, and it's still a slowdown by 10% on build. Not great, I admit it. This shows some of the current limits that our pipeline have when we're dealing with hundreds and hundreds of modules, especially around resource pipeline. But that's something we're working on. And note also here that this is not showing anything from 3.4 and 3.5. But the clean build doesn't necessarily represent your day-to-day build. When you build multiple times a day, hopefully, a lot of those builds are incremental. And so if you look again at the Spotify change, the Spotify project, the incremental build actually got faster by 37%. And if I normalize again on the growth from line of code, it was actually 2 times faster. Not too bad. It actually shows that making sure everything that can be incremental actually is really important. And as Xav mentioned, when we add cacheability to the mix, it's even better. And so you see here with a lot of improvement we made to cacheability to the task, the Spotify build cached this time improved by 50% while the project was growing. So again, to normalize with the growth of line of code, that's about 3 times faster if their project had not grown in the same time. So hopefully all those graphs show you that we are working very hard to keep improving build speed and help you get more productive. And the first and best tip to get your build speed down is to upgrade to the latest Android Gradle plugin version. But we know we still have a lot of work to do, mainly around configuration time, resource processing, especially as I mentioned, on those projects with lots and lots of modules, and continue to improve parallelism. But that's not all. We know that many of you use additional custom Gradle plugin, and we want to help there too. So for that, we're working on a build speed attribution tool in Android Studio. The goal is to help you understand which plugin and which task are actually affecting your build speed most and what you can do about it. Because sometimes you're using a plugin that we don't write, so we want to help you tell the plugin owner, if it's you or someone else, what's going wrong and what they can do to help. And this will be in Android Studio very soon.
All right, so we're going to talk about some tips and some tools about helping you better configure your project. So the first thing I want to mention is that configuration should really be fast. I talk to developers a lot. With developers who tell me that their configuration is fairly slow. I actually talked to a developer just today telling me 150 module, almost 10-second configuration. And this is really not in line with what the baseline should be, right? So we wanted to look at how fast should configuration be. So using the same project that's about 100 modules, and those modules don't do a lot of configuration, right? There's only one plugin, the Android plugin, and it mostly set up some dependencies and nothing else. And so when we look at configuration using build scans, we see that the configuration takes about a second, which adds up to about 10 milliseconds per module. Now, of course, the task graph computation is there too, but depending on what you're building, you may not do all of it. But here, for a large, for building the whole app, we see about under 2-second configuration. So if you have 200 modules, you should see 4 seconds. If you're already seeing 5, 10 seconds, and you have 10, 20 modules, clearly something's happening. Right? And it's actually hard right now to figure out exactly what's happening. But be aware that basically every code that you put in your DSL, right, because it's code, will add time. And there isn't a whole lot of way to make that faster. Right? The best way to do it is just run a JVM profiler and see exactly what's happening. You may be using some plugins that do things that they shouldn't be doing, that are just slow. And of course, I mean, there's a few obvious candidates, right? Don't resolve all, dependencies during configuration. Don't configure all the tasks eagerly. But really, the only way to do that, if you're using third-party plugin, is to profile it somehow. So in terms of speed, to increase your build speed, we'll still recommend doing several modules. And Jerome talked a lot about workers, how you can get parallelism for worker. But he also showed that workers have some limitation, right? You have to spawn them from your task, and while you're doing that, you can't run any other task. And so you're always going to get better parallelism for multiple modules, so you should still try to go there. In addition to that, we see more and more developers actually using caching, distributed caching or local caching. And so imagine if you have a few local changes, and then you rebase your changes on top of some changes coming from upstream. If you have a single module, well, if you have some Java files that have changed, you're going to have to rerun the whole Java compilation. If you have 100 modules and you only have a couple, maybe 3, 4, 5 modules that are touched, all the other modules are good candidates to actually get the output directly from the cache. So you have better cache granularity and more likely to get faster builds from that. And then the other aspect of it is compilation avoidance. None of the projects we showed in your benchmark actually use compilation avoidance. But it's a very useful tool. So I want to run through a scenario that explains a little bit what compilation avoidance is, because we still see some developers not really understanding what's going on. So let's say you have an app that depends on library 1, that depends on library 2, that depends on library 3. And so we want to see the impact of compilation avoidance when library 2 declares its dependency on library 3 one way or the other. And so we're going to look at it by looking at a bunch of tasks. Compilation task, dexing, whether using Java 7 or Java 8, it actually has a difference, and then packaging. All of that when you do a code change on library 3. So by default, of course, if you do a change on library 3 is going to have to run its dexing, whether it's Java 7 or Java 8, and then at the end, you're going to have to package everything. And none of the library are involved in the packaging, so it's only affecting that particular module. So let's say you do a code implementation change, right? So you just go in the library 3 module, and you just change the content of a method. Gradle will do compilation avoidance for you automatically. So it will detect that the API of library 3 did not change, and you will not recompile either library 2, library 1, or application. It works out of the box. It doesn't really matter whether you use API or implementation for dependencies. It just works. Great. That's kind of like really your best case scenario. Right? Now, if you do a change in library 3 that adds a public method, and I'm talking here about adding it without actually using it, and you've declared library 2 as an API, library 3 as an API of library 2, then you're going to recompile everything. Right? So you're going to run compilation on library 2, library 1, and app. Of course, the output is going to be the same. So at least in the case of Java 7, you don't need to run dex again, right? Because Gradle will look at the input of dex and will say, well, it's exactly the same thing that I had before, nothing to do. However, for Java 8, that's different. The desugaring process has to look at the dependencies. So when it processes library 1, it has to go and look at library 2 and library 3, what their API is. Is it using some language feature that it needs to desugar, and therefore it impacts the output of library 1. So you have to redo everything. Now, if you change the dependency from library 2 to library 3 using implementation, you save a little bit, right? Basically, what you're doing is you're telling the consumer of library 2 that library 3 is hidden from them. So app and library 1 do not see library 3 at all. So automatically, you don't run the Java compilation on them. However, right now, we still do predexing in the case of desugaring. That is actually a problem in our plugin that we need to fix. But once you do that, then you will also not run dexing, right? Which is important because especially in the case of Java 8, when you use Java 8 language features, we have to run it very often. It's extremely hard to try to reduce the cases where you're not doing predexing. We are doing it very often as soon as an API change. And here, I'm not necessarily talking about an API that matters to app and library 1 and library 2, right? You could have a public class with a public method that you only use internally in library 3, and it's still going to go and trigger a bunch of changes in your consuming modules. So compilation avoidance is very useful. Start using it. It's going to get better as we improve the plugin, and it's really going to make your build faster. Some caveats to parallelization. We see some developer telling us, yeah, I have 10, 20 modules. And then they say, well, I have one big app module with like 90% of my code. That's not helping. You should really make as small modules as you can. And then as Leo mentioned earlier, our resource pipeline is not very efficient for multi-module. In fact, if you see the chart that he shows for resource change for large module with one module and with 100 module, the 100 module is slower than one module. That's temporary. As we start working on namespace again and additional changes to our resource pipeline, we'll get much better performance in multi-module builds.
All right, so how can you understand your build performance? I mean, we all know that the Android build system is a very open environment. You're not constrained. You can have your own plugins. You can have your own annotation processors. You can write code in the build Gradle. So all these things compound to each other, and eventually, it's very difficult for us to deliver something that we know will perform well because you can customize it to no end. So you need tools to be able to understand how these things work. And so you've got already a few tools that are provided by Gradle. The Gradle scan is one of them. It's very effective. It will give you information about why the tasks run, what were the dependencies. All this kind of information will be given to you. One of the only caveats that it has is that it forces you to upload some information to the Gradle servers. So this information contains things like file paths, file names, variant names, and stuff like that. So we understand that not everyone wants to send this to the external world. So therefore, there are some other tools. The profiler is another simpler tool that you can use. It will still give you information about why your task ran and all that kind of stuff. It's not super visual, but it's still interesting, and it's still something you should consider using. But to help you further, we developed an ability to have Chrome trace being generated out of your builds. So what we do now is that we are capable of generating these, and we can display very visually all the tasks that are being scheduled per thread. So you can see here on the left-hand side the thread numbers. You can see the task here. You've got, for instance, the task in magenta, which is the merge resources. You can even see the workers which are spawned for that particular task executing. And by the way, you can see here visually that as soon as the task is done spawning the workers, the next task can start, which is the process application manifest in green. So you can see how here, very visually, how then your task can be running in parallel, even within a single module, because here there's only one module. On blue here, you've got threads. These are threads which are just used using the executor services. So this gives you a very good visual, again, about how we use the JVM resources. You can even go a little deeper. For instance, here you can see that the task execution span is this magenta color. You can see that there is the up-to-date check. So that's the time that Gradle will spend to figure out the files which are out to date. Then you've got the task implementation, which is the all phases. So that's really the code of the task itself. And then we even further down, we kind of split it even further to get the different phases. So that gives us a lot of information about how those tasks are implemented. So this is for our tasks, obviously. If you were to run this Chrome trace with a different plugin or with your own tasks, you will see your tasks as well, but it will not be as descriptive as this. Nevertheless, it will be still very interesting visually to figure out where those tasks belong and so on. So now if you face yourself with the impression that your build is slow, which I'm sure is 99% of you, we would really recommend that if you want to file a bug or tell us that the build is slow and it should be improved, that you provide us at the very least this Chrome trace so that we can visually look into what's going on. There is no PII information. We don't have file names. We don't have task name. We don't have variant names. There's nothing in there that should be of any concern. This is the same data that we use. That's the data that we upload to our server. So if you opted in the server that to the data that Leo used to do all these graphs earlier, you don't share anything else. So to have the trace enabled, you just need to add this property. And then you will find a JSON file inside the build Android profile. That JSON file, you can use it in Chrome. You can load the Chrome tracing facility in Chrome, and then you can load that file, and then you will see exactly what I just displayed in the previous slides. Again, this is super visual, very useful. It taught us a few things when we started looking at this even ourselves. So I totally recommend that if you have a very sophisticated build, you try this, because you might get some few surprises here and there. And with that, I'd like to thank you for coming today.